Hello everyone. Welcome to the fourth interaction session of network analysis. I'm your TA Dipannita. This week sir had taught about what would happen if a time varying voltage is applied in a inductive circuit and introduced like how the EMF is induced in the coils. You were taught about what is the self-inductance and the mutual inductance and like different dot convention of mutually coupled circuits. Various series and parallel circuits were discussed and the energy stored in it were discussed. So in this tutorial we will be covering all those topics. We'll be solving 4-5 numericals based on that. So before you go into it, the few things that we are going to be using throughout the session are like it is very essential that you can write the voltage or the current whatever equation like loop or branch equation when the inductors are specified, like the dot convention of the inductors are specified, and depending on the way they are connected, you can write the equations. So let us just first look into how to write those equations, and then we will move into solving the circuits. So for the basic like one is two inductors when they are connected in series, right? So this is one of the inductor, and this is another inductor with inductance L1 and L2, and they are connected in series with the dot given here like this. So in this case what will happen is like when a current like when a voltage is connected across it, so there will be some voltage that is connected across it, V of t. So just so because of this voltage there will be a current introduced into the circuit. So this current will enter through this particular L1 through the dot, and also it will flow like this, right? Because they are connected in series, so both are entering the dot. So because of this there will be EMF introduced into the both the inductor, and if there is any mutual inductance between them which may be denoted by M, that will also have to be accounted. So if you remember, sir had taught like there will be the EMF that is introduced. Let's say suppose this point is A, okay, so this will be the uh, self inductance that is introduced into the circuit, and this is the mutual inductance. Since the current is same here in both, so it will be di by dt only. uh, if anyone is unmuted, if you want to ask anything you can, otherwise mute yourself. Okay, this 2 will be for the coil 1 and this 2 will be for the coil 2. So let's see if anyone has anything to. So somebody is unmuted, can you? Yeah, Murshid, could you please mute yourself? Yeah, thank you. So the sign of this will depend on like how the dot convention is given in the circuit. In this case, the dot convention is given in such a way that current is entering in both the circuit. So initially for the self inductance, as current is moving in this direction, it will be plus and minus. A voltage drop will appear across this. This V will be equal to L di by dt, right? And the mutual inductance. So guys, do please join in time, otherwise it's difficult to move back and forth. Okay, so we were talking about now the convention of the mutual inductance. So which way will be the positive one? Will it be this side or this side? Can you comment? Can anyone comment? Sir has shown in his lecture by Lenz's law this particular thing, right? So whenever, like, just remember, whenever the dot convention is such that the current in both the case it is entering, so it is in the same direction as that of the self inductance, right? So it will be plus minus m di by dt. In the case of second one also, there will be a voltage drop like this, and the mutual inductance will also be like this, right? This will be L1, this will be L2 di by dt, and this is m di by dt. Now to in during the case of circuit solving, it is this time domain circuit is converted into frequency domain, so that it is easier to write in form of phasors, and we can solve the equations easily, right? Because differential equation will take time to solve, right? So instead of L1 di by dt, it is written as L1 j omega I. So this di by dt is written in terms of j omega I, right? Similarly, in this case, it will be m j omega I. Omega will be the frequency of the, like, it will be the whatever
Ma'am,
the,
your voice is not audible, ma'am.
it's not audible. Let me check. I'm so sorry. I have muted myself somehow. Is it audible now?
Yeah, yes, ma'am. Now it is audible.
So all this time you couldn't hear me, right?
Yes, ma'am. Now only we are hearing you.
Okay, okay. So I was just talking about like two inductors in series, like when their dot convention are such that in both the cases current is entering. Since they are in series, this is one single current that will be flowing through the loop. So how their voltage drop across, like induced EMF of across the inductor will be, and that will create the voltage drop. So this is given like for the first coil, it will be a voltage drop. Since current is flowing in this particular direction, so the voltage drop will be like this, right? Which will be equal to L1 di by dt. And because of the presence of this another inductor, there will be flux linkage, and this particular term, if the mutual inductance between these two circuit is given, then you will be able to calculate the uh, term contributing from the mutual inductance. Now the direction of that drop will depend on the dot convention that is given. Since in this case both the currents are entering through the dot, it will be in the same direction as the self inductance. So it will be plus minus. There will be a voltage drop like this, which is given by m di by dt, right? So similarly, in the case of the second coil, there will be another voltage drop L2 di by dt. Is it okay? Because the current is entering through the dot here, so of course there will be a voltage drop like this VL, so which is given by L2 di by dt. Because in inductor we know, right, L di by dt is the voltage drop. This is the self induced EMF that is getting generated. Again, for the mutual inductance, since both the cases the current is entering through the dot, the sign of the mutual inductance will be in the same direction as shown here. So I guess you have seen this in Sir's lecture, like he has talked with respect to the flux that is flowing and the how it is getting linked, and like it is using Lenz's law to oppose the very cause of the change. In this case, this change is this Vt, which is an external excitation that is getting applied, which is time varying in nature. So you guys have seen that lecture, right? I mean, I have to assume you have seen it. So now like we have to convert, like when we solve the equations of the circuit, it is difficult to solve in terms of like a differential equation, right? So we converted it to the frequency domain. So this di by dt is written in terms of j omega into I, right? This is in terms of frequency domain. So it's the same thing for mutual inductance, it will be m j omega I. In this case, this will be L2 j omega I, and this will be m j omega I. In this case, all the current is I because both the inductors are connected in series. So the net equation will be V of t will be equal to, so if we apply KVL in this single loop that is given here, it will be L1 j omega I plus m j omega I plus L2 j omega I plus m j omega I. This is similar to this differential equation, which otherwise we would have written as L1 di by dt plus m di by dt plus L2 di by dt m di by dt. So if we just since di by dt is common here, it is L1 plus L2 plus 2m di by dt. So it is some sort of an equivalent resistance into di by dt. So it is similar to a like an inductive circuit when it has a certain equivalent inductance, how the current is flowing. This is the equation describing it, right? Now there is like a second case to this would be when the dots are opposite, like one dot convention is given in this way. Again, it is the same circuit. Okay, so there is a voltage that is connected, V of t, and there is a current I that is flowing. Now in this case, you see for the inductor 1, through the dot the current is entering. However, in this case, through the dot the current is leaving because this is the single current that is flowing, right? So in this case, what will happen? How will the voltage drop be? So let us consider this is for the inductor 1 and this is for the inductor 2. So how will it be? So again for the first circuit, the self inductance will be L1 di by dt. Now how the sign will be? The current is entering through this terminal, so the voltage drop will be like this. In the second circuit, again the self inductance will be L2 di by dt. And since current is entering through here, so the voltage drop will be like this. For the mutual, if the mutual inductance is given as M, uh, just hold on. So the mutual inductance will be di by dt, but what about the sign? Since these two, the dot convention are opposite in direction, that is in one side like it is entering, the other side it is leaving. That means what? When this part is in the positive, like what this dot convention means, when this side, this particular point is positive, this particular point will be positive. Sir has taught in the class like using like using Lenz's law and all, he has shown like how this mutual inductive sign is determined, right? So in this case, when the dot convention is like on the opposite end, like the current is once for one coil entering the dot, in the other time it is leaving the dot, then the mutual inductance will be, the sign will be reverse to that of this voltage drop. So it will be minus this side and plus this side, m di by dt, right? So if you solve it in the same way, in this case, you convert it into frequency domain and get it. So Vt will be somewhat like L1 plus L2 minus 2m. You use the KVL once again. So it will be this net equivalent inductance times I. So the reason why I am showing this is we will be using these conventions while solving the circuits. Is it making sense to everyone?
Ma'am, I have a doubt.
Yes.
Ma'am, in the second inductor, you
Yeah.
have shown that mutual inductance M di by dt, you are using it as minus plus
Yeah.
symbol.
Yes.
But current in the first inductor, it is flowing from through the dots, ma'am. It is not leaving. So how did you put minus plus instead of plus minus, ma'am? That is confusing actually here. In this, while writing for the first inductor, you told
Okay.
that current is leaving from the dot, so I have used minus plus. But here in the second in the diagram, mutual inductance has been written like the current is actually entering, ma'am. So whether it is plus or minus plus, ma'am, that is
So
actually confusing.
so the thing is, like in the mutual inductance is actually how one of the inductors sees with respect to the second inductor, right? So irrespective of like since the current is leaving through this dot means what? Like suppose we had like as sir has taught somewhat like with a square convention. So dot means like whenever this particular point is positive, this particular point of the circuit will be in the positive voltage. Here shown in terms of windings, right? Like there is a one common magnetic core and there are some windings like this. So basically what happens is whichever the direction the current will flow, the self-inductance voltage drop will be same. It is like in the direction when the current is flowing, it will be in that direction, the voltage drop will be there. However, for the mutual inductance, in this case, you see this inductor as it is seeing the other inductor L1, it will just be opposite in sign to what the self inductance was, because it will oppose the very cause of that change. In this case it will oppose the flux that it getting generated because of the first inductor to the second inductor. Because of the current flowing in the first inductor, there will be a flux generated in the second inductor, and will that flux will get opposed by this particular mutual inductance, and hence it will have a reverse sign. Did you get it? Like in
I'm
both.
getting it, but you are telling for self-inductance, you put plus whether you have any side dots, but for the mutual inductance, if it is opposite to the other one, you have to use minus plus.
Yes, yes. Because in case of mutual inductance, it is what? It is one of the circuits saying what the other circuit is doing. So irrespective of which which inductor I look into, the other one is like in the opposite of what this circuit is. So it will always
Okay,
be
fine
minus.
and clear.
Yeah.
Okay, okay.
So this is in case of series. Any other question? Okay. So the other two types of circuit that we'll be using in our uh, problems are when there is a primary winding and secondary winding connected as shown here. So in one case I1 is flowing, in the other case I2 is flowing because of the voltage. Suppose there is a voltage V of t connected across this, and there is some circuit that is connected here. I'm not drawing it because it won't be of relevance. So now for this circuit we have to see how the voltage drop is. So in this case, so there will be a self inductance and a mutual inductance. So in this case, the self inductance, so let this be L1 and this be L2. So L1 di1 by dt, right? In this case, what will be the mutual inductance? Suppose this is M.
M di2 by dt.
Yes, di2 by dt. Now about the direction. Since the current is flowing like this, so there will be a voltage drop like this. In case of mutual inductance, also you see like in both the cases, the current is entering through the dot. So it will be a voltage drop like this. So in the previous case, one thing you can imagine is, like, if you are getting confused about why the direction is like this, instead of that I'll use a different color. Wait. Instead, imagine some current in this direction that is minus I. So if you imagine that, then even if you consider a voltage like this, it will be m d of minus I by dt, right? So basically it will be minus of m di by dt. So even if you take the direction like this and it is coming some negative quantity, so that means what? The direction is actually reverse. It should be minus this side and plus this side. Then you can write it as m dy by dt. You can imagine it that way also if it helps. So for this case again, so it is m di2 by dt, right? Uh, for the second inductor, actually it will be kind of similar, since current is entering like this, so it will be, there will be a voltage drop which will be L di2 by dt, and there will be a mutual inductance M di1 by dt because of the inductor that is there in the primary winding, and the direction will be, since both are the dots are entering, it will be like this, right? It's fine. So for the next one we will take the reverse case. That is, in one of the circuit, the current will leave the dot. So it is leaving the dot, I2, this is I1. So to make the convention easy, I will imagine as if one current I2 minus I2 is flowing in this direction, right? If we imagine that and use the same convention that we have used here, you will see what we come up with. So now what we do is, for the first circuit, let us draw the self inductance and the mutual inductance. So the self inductance will be again L1 di1 by dt. The mutual inductance will be M2 d. Now we have imagined that minus I2 current is entering the branch. So in this case we have imagined both the currents are entering the branch. So let us just for now write it like this is the voltage. If this was the voltage drop for the first inductor, the self inductance, let us just write the convention like this. However, in this case the current will be minus I2, right? Minus di2 by dt. So this comes out to be minus m di2 by dt. So since the voltage is coming as a negative value, that means what? Actually the convention is like this, negative this side, positive this side, m di by dt. Is it okay? Is
Yes,
it?
ma'am, it is clear.
Yeah, okay. So again for the second circuit it will be, so either you imagine a minus I2 current coming through this way and write like this one is minus L2 di2 by dt in this direction, and m di1 by dt in this direction, or getting rid of minus I2, it will be, the convention will be changed, L2 di2 by dt, and this is plus minus m di1 by dt. So this is clear, right? This is what we will be using while solving the circuit problems in our class today. So can we, if anyone has anything to ask, you can ask. Otherwise, we can move to the first problem of our lecture today.
Ma'am, please explain the second that minus L2, ma'am. Minus L2 di2 by dt.
Yes, yes. So where did my pen go? Yeah. So we are imagining that a current minus I2 is entering this dot, right? So that means what? The self
Okay, ma'am.
inductance
Okay.
will be L2 d minus I2 by dt, right? So I'm just
Yes,
taking the
ma'am.
minus outside and then reversing the sign.
Okay,
And
ma'am. Okay, understood.
yeah, then like in the question, like there will be a voltage that is getting connected here, so you apply KCL. There will be other circuit that is connected to the secondary, like here some resistor or anything is connected. Depending on that, you can solve the circuit and get to the whatever the parameters that are asked in the question. So anyone has anything else to ask? Okay, then let's move to the first question. So there is a circuit given in which the primary is connected across a 100-volt sinusoidal, the RMS value is given as 100 volt. It is connected across the inductor which has an inductance of J36 ohm, right? There is a current I1 that is flowing and it is entering the dot. In the secondary, there are two different coils in which in one of the coils the dot is in, like in one of the inductor, the current is actually leaving the dot and the current is flowing and coming in this direction, and in the third coil the current is actually entering the dot. So the mutual inductance between coil 1 and coil 2 is given, and the mutual inductance of coil 2 and 3 is given here, and this one is given for coil 1 and 3. So all the self inductance and the mutual inductance are given. You have to estimate what is the value of I1 and I2. That is, we have to solve one KVL equation for this loop and the second KVL equation for this loop. So let's solve one at a time. So for the first circuit, which is like connected to a external voltage, an external time varying voltage, right? It is given as 100 volt. So we will convert this time domain equation into frequency domain, because all the reactance and all are given in terms of the uh, in terms of J, right? So this is in frequency domain. So voltage is, since no angle is given in the voltage, so we will consider V of t to be like the RMS value to be 100 with angle 0, like there is no angle, right? Now in the first loop, how will the self and the mutual inductance be? Like in order to avoid mistake, you may just write down the voltage drop and then solve the circuit. So in this case, so there is a voltage drop, a voltage connected of 100 magnitude connected in along this coil, and this coil will have a self inductance. In this case, what is the self inductance here? It is 36 ohm, right? So in this case, L1 di1 by dt is actually J into 36 I1, and since current is flowing in this direction, so the voltage drop will be like this. Now okay, now the thing is, there will be three other voltage drops because there are two mutual inductance corresponding to the two different coil in the secondary, right? So there is also another coil in the secondary. There will be the mutual inductance because of the first coil, and it will be di2 by dt. Now either, since we have seen in the previous where we have written the different sign convention, so these two are opposite, like here the current is leaving through the dot and here the current is entering through the dot, so the sign convention will be reverse, right? Minus this side plus this side. Is it fine? Is,
Yes, ma'am.
yeah. So the mutual inductance is given as 8.4 into I2. It is given
Ma'am,
here. Yes,
Uh, Ma'am, you write L1 di1 dt is equal to J36 I1, right?
yes.
Why uh, why did you not write di1 by dt?
So the thing is, we are converting like the time domain circuit like L di by dt into frequency domain. That is L j omega I. We are converting the time domain circuit to frequency domain.
Okay, ma'am. Ma'am, but there is already available J
So yes, so L omega is given because Xc is what? Xc is 2
omega
pi
L.
f into L or omega into L.
Yes, ma'am.
This will be what will be the unit of this in ohm, right? Because L is in Henry. But if you
Yes.
write Xc, it will be in ohm. So this omega L value is given as 36. So in place of omega L, we write J into 36 and whatever the current is,
Okay, ma'am.
right? So that is
Okay,
why
ma'am.
I have written it J36 I1. Similarly, in case of M12, so M di by dt can be written as M into j omega into I dash whatever. In this case, it is I2. So this M omega value is given as 8.4 ohm. So it is 8.4 j into I2, which I have written here. Clear?
Hello, ma'am.
Yes.
X is equal Xc is equal to 2 pi fl or XL is equal to 2 pi fl.
Sorry, XL. I meant XL for the inductor, the impedance. Yeah. Is it fine?
Yes, ma'am.
Okay. Then for the third, like voltage drop will be because of the third inductor that is present here, right? And the third inductor has a mutual inductance of again 8.4 ohm. So di2, because the same I2 current is now actually entering the dot. In this case, you see the current is entering the dot. So the direction will be in the same direction as that of the self inductance di2 by dt. So it is also 8.4 I2. You see the convention, right? Because in the third inductor, I will highlight this one. Wait. So in this third inductor, the current I2 is flowing into this dot, right? And it has a mutual inductance of 8.4. So the sign convention is this direction. Whereas in the coil number 2, it was reverse. Are you getting the sign convention properly?
Yes, ma'am.
Yes. Now,
Yes, ma'am. Here, M13 di2 by dt is equal to J 8.4 I2 I
yes,
think.
yes, J will be there.
Okay.
Yes. So now that you have written in terms of all the voltage drops, you can apply a KVL across this loop, right? So it will be 100. If you are moving in this direction, it will be J36 I1. Then you come across come across the negative sign, which is this term. So it will be plus J 8.4 I2, and then you come across this one, right? So it will be minus J 8.4 I2. This is equal to 0 by applying KVL. So these two terms will get cancelled. We have I1 equal to 100 by J into 36, right? So 100 by 36 is 2.77. the magnitude is 2.77. Now 1 by j can be written as j by j square, and j square is equal to minus 1, right? So it is 2.77 j. Is it fine? So the RMS value of I1 will be equal to 2.77. Since the angle is not given, the phase of the current vector is not asked, you don't need to calculate it. If it is asked, you convert minus j into angle and you can write accordingly, right? So it is like you understand, I1 can be expressed as 0 plus minus 2.77 j. So you have to calculate the magnitude, which will be equal to the RMS value, since we have taken 100, which is in volt, the voltage which is also in RMS value. So we get the magnitude as 2.77. Is it okay?
Yes, ma'am.
Yes, ma'am, it is clear.
Okay. Now we move into calculation of I2. So let me move to the next page. So for calculation of I2, you have to apply the KVL in this particular loop, right? So I1 we have calculated as minus j 2.77. Now for this loop, again you can draw the equivalent voltage circuit. So this is for the second inductor, which is given here, and then this is for the third inductor, and there is a resistance connected, 40 ohm, and a current I2 is flowing like this. This point is that A point, this is B, and this is C. Now tell me, okay, let's start with the second one, how the voltages will be. For the self inductance, it will be L2 di by dt, di2 by dt, which is equal to, it is given J4 ohm, so it is J4 I2. Now how will the sign be? So the current I2, it is flowing in this direction and then coming in this direction, right? So actually, if I consider this second inductor, if this is point A, current is actually coming like this. So the voltage drop will be positive in the A side, negative in the B side, right? Because current is flowing in this direction. So it will be plus this side, minus this side. Is it fine?
Okay.
Then for the mutual inductance, which is because of the first inductor, di2 dt. In this case, the dot convention shows that these two are opposite. Like in one case, the current is entering through the dot and the other current is leaving through the dot. So the mutual inductance, which is given by 8.4, because of the first coil, what will be the convention? Could you tell me, like, let's consider this side to be the B side. So which side will actually be positive and which side will be negative?
A side negative
A
and
side?
the B side negative.
Uh, how?
Ma'am,
Note that these two are in the opposite direction. So in, like, let's look into, in this is case, this 4 scenario, right? So in this case, you see, for the secondary, the mutual inductance will be in the reverse direction, right, of the self inductance. Did you follow this part, right?
Yes.
So in this case, it will be just so the self inductance is positive this side and negative this side. So in this case it will be in this direction, right?
Ma'am, whether M21 di1 by dt or di2 by dt, ma'am.
di1. It will be di1,
Okay.
which is the current flowing in the primary. So it will be 8.4 J into I1. Now for the third coil, it is M31. In this case, it will be di2 because it is the same current that is flowing. This is kind of like, if we consider the coil 2 and coil 3, it is like two inductors that are connected in series but having opposite dot convention, right? So again, in this case, yeah. So in one case the current is flowing out, in the other case the current is flowing in. So how will the sign convention be for M31? Let's consider this is C, this is point C, and this is let us consider this is point D, and this is
Excuse me, madam.
yes,
Madam, third voltage M31, it should be, I think, M23.
yes, it is 2 3. I'll rub it off. Yes, it is 2 due to the third coil. So the point D will be positive or negative? Can anyone say?
Positive.
Yes. So the voltage drop will be like this. So now that you have the feel of the first like inductor, can you also write for the second inductor quickly?
Yes, ma'am.
Yeah. So for the second inductor, the self inductance will be, so current is entering through this particular terminal. So it will be plus this side and minus this side, and the value will be L3 di2 by dt, which is given as J49 into I2. Now again, because of the first inductor, how the how the flux is changing in the third inductor, and due to which the mutual inductance is given as 31 di1 dt. Now how will the sign be? Since in this case what is happening, in both the cases it is entering the dot. In coil 3 also current is entering the dot, in coil 1 also current is entering the dot. So how will the sign be? Let's say this side is E and this side is F. What will be F and what will be F?
F will
Plus.
be positive.
Yes, F will be positive, E will be negative, and this value is given as J8.4 I1. Now for the last one, M32 di2 by dt. So in this case again it is opposite in sign, so the sign will get reversed and it will be given as 11.2, right? 11.2 J I2. Now you have all the voltage drops, and the voltage drop across this particular resistor will be 40 into I2, right? So you have all the voltage drops, you can apply KVL and solve quickly what is I2. Can you guys try this one? Let me know the
Yes,
value.
ma'am.
Let me know the value when you get it. Okay. So yeah, I'll start. 49 J I2 minus 8.4 J I1, then plus 11.2 J I2, then we go to the second one, which is
Ma'am, I2 is 40 plus J53.
Uh,
I2
let's
I2 will be
calculate.
0.
Yes, I2 will be actually 0.
0.
Yes, so I'm solving it. So I'm using KVL in the loop.
Yes, ma'am. Yes, ma'am. It will be 0 because uh, they will be going in.
I1 terms gets cancelled, right?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Minus 40 I2. This will be equal to 0. So this I1 and the other I1 terms gets cancelled. So it will be a lot of terms into I2 is equal to 0, right? So I2 will be equal to 0.
Yes, ma'am.
Okay. So we have now calculated I1 and we have calculated I2. Now what is asked in the question is find the voltage, RMS voltage difference between point A and point B. So can you calculate this? What will be equal to VAB? So basically what is the voltage across this, right?
Madam, can you please once again explain the I2 value calculation?
Okay, so I'll do it then step by step. So yeah, we are now applying KVL into the equation, right? So we are this particular loop, like this particular loop, we are moving in this direction, okay, along the direction of the current. So the first voltage that we encounter is J49 I2. This is voltage, right? So this side is positive, this side is negative. So we are like you can take any direction, like one direction you fix it. So in my case, if you are entering through the positive, I am taking it as negative. So it is minus 49 I2. Then the next one we encountered is 8.4. Again we encounter positive direction. So minus 8.4 JI1. Similarly, 11.2 we are entering through the negative direction, so it is plus 11.2 JI2. Similarly, for the rest of the three voltage drop here, and then finally across this particular resistor in which the voltage is 40 I2, so minus 40 I2. Now this I1 and I1 terms get cancelled. So the rest of the term that we have are minus 49J, then plus 11.2J plus 11.2J, then we have minus 4J and minus 40. All this has I2 terms, right? So if we take the numerator on the other side, it will be I2 0 by whatever, it is equal to 0, right? This particular term will come here, minus 49J whatever, so it is equal to 0, right?
Okay, madam, thank you.
Yeah. So let me see if I can take this circuit there. No. So now we have been asked to calculate the value of VAB. So VAB will be, if we move along this particular direction, it will be
0.
No, ma'am.
no.
23.268.
Yeah, because there will be some I1 term here, so it can't be 0. So so whoever has calculated will start doing it. So first one is this M23ID2, which comes out to be 11.2 IJ. So let me just redraw it here. So this is VAB. So positive this side, negative this side, right? Here it is 11.2 JI2. Since I2 is 0, this will be equal to 0. So 8.4j I1. So I1 has a finite value, so it will be 8.4j into minus 2.77j. Then again in this case it is 4j I2. Since I2 is equal to 0, this voltage will be equal to 0. So this will have a voltage of 8.4 into 2.77. So let's calculate that. 23.268. Is that what you got?
Yes, ma'am, I got that value.
Yeah.
Ma'am,
So yes.
minus 23.35 or 23.35.
So you see there is a minus sign before 2.77. So this will be a negative quantity into j, right? Because there is 1j here, 1j here. So j squared is equal to minus 1. So this will be minus of 8.4 into 2.77 into minus 1, right?
Yes.
So it is 23.268. So let me see if I did it correct. One second. VAB. Oh, I think it will be minus. Okay, I get it. So
Yes, ma'am, it will be minus, ma'am.
yeah, it will be minus because like this voltage itself, like the direction, if you see here, so I'll zoom it here. So it will be positive in the direction and negative in this direction. So the voltage is actually like this. So sorry, this will have a negative sign. So it will be minus 23.268. So is it okay with everyone?
Yes, ma'am.
Okay. So we can move to the next question, right? So for the next question, it is given like the previous question and this question are both like they have a second. The previous question had a primary winding and secondary winding. In this case, there is also a tertiary winding, and there are current that are flowing in the three different separate loops, I1, I2, and I3. So you have to estimate, you have to calculate all the values of I1, I2, and I3, and finally calculate V1, V2 and V3. So it is just the same problem like we did before. Only thing is there will be three loop equations because there are three different loops, right? So should we start solving?
Yes, ma'am.
Okay. So for practice, you will tell me like what will be the sign conventions and all, right? So we are drawing first the first loop. So there is a 100-volt RMS connected, and there will be a self inductance that will be introduced, L1 di1 by dt, which is equal to, it is given here 16j, so 16j I1. How will the sign be? So let's say this is A, this is B, this is C. So A will be,
Positive.
yes, and because the current is entering through this direction, so there is a voltage drop. Now because of a mutual inductance between the first coil and the second coil, there will be di2 by dt, which is given as 9.6 in the question. So it is 9.6j I2. Now tell me the direction. B will be,
Minus.
yes, because in this case the current is leaving through the dot, so it will be reverse. So you can from loop 1 you can write the equation as, so if we move along this particular direction, it will be 100 minus 16j I1 plus 9.6j I2 is equal to 0. This is the first equation. Now if we consider loop 2, so the loop 2 has two inductors and each of it will have a self-inductance and a mutual inductance. One has linkage with the coil 1 and the other one has linkage with the coil 3. Sorry, I mean the third loop, the coil in the third loop. So in this case it will be, I'm directly writing the value. So the self-inductance will be 49J into I2. So the current is entering the dot. So it will be, the sign will be in this direction. Now for the mutual inductance, which is given as 8.4 here, in this case, in this, let us name this coil as 3 and this coil as 4. So in coil 3, the current is entering the dot. In coil 4, the current is leaving out of the dot. So the mutual inductance sign will be changed and it will be 8.4 JI3. Right? Now for the coil 2, so again in this case the current is entering in this direction for this particular coil, right? This I2, it will flow and enter like this. So the self-inductance voltage will be, so I will name this as point D, this point as E and this point as F. So self-inductance is 3.6 J I2. Now tell me what will be the sign of D?
minus.
Yes. Oh, sorry. Yeah, minus. You're right. Because current is entering through this direction, so the voltage drop will be like this. So this is plus and this is minus.
Madam, there is a 3.6 or 36.
Oh, sorry, it is 36, right? So 36. Thank you. Okay. So for the mutual inductance, it is given as 9.6 I1 since it is linking with the coil 1, and in this case the dot convention is opposite, because in this case the current is leaving the dot, in this case it is entering the dot. So E will be, now the E will be, what is the sign of E?
Positive.
Yes. So I guess you got the hang of this now. So now we write KVL in this particular loop again. So we write KVL. So it is 9.6 I1 minus 36 I2, then 49 minus 49 I2. So there will be J with each of it. 49 I2, then plus 8.4 J I2. So this equation contains terms between I1 and I2. So we can write one in terms of the other. So if we remove, like, this will be equal to 0, right? So the J's can all be taken as common and
The last one is
gotten rid of.
I3,
So
8.4 I3.
sorry, yeah, it is I3. Okay. So it is a equation between I1, I2 and I3. So let's at least substitute one of them. So let's write I2 in terms of I1 and I3. Okay. So 36 plus 49 is 85. 85 I2 equal to 9.6 I1 plus 8.4 I3. Let this be equation 2. This is fine, right? So the we need another equation because there are three variables, so that will get from the third loop. So I'll just copy the circuit. So for the third circuit, again we write the voltage drops. So current I3 is flowing in this direction. So the current is actually leaving the dot in this case. So the self inductance will be J4 I3. And the mutual inductance, so in this case current is entering and in this case the current is leaving, so it will be in the opposite direction again. So it will be 8.4 I2. Now what about this capacitor? So this VC will be 1 by 2 pi FC, right? Or 1 by omega C, sorry, this XC. So the voltage will be I into XC, sorry, it will be I into J omega C. Now this particular factor is given as minus J15, right? Is it fine? So the voltage here will be minus J15 into I2.
Ma'am, it is I3, ma'am.
Sorry, yes, I3. So then again apply KVL in this loop. So you will get an equation in terms of I2 and I3, right? So 8.4 JI2 minus 4 JI3 minus of minus 15 JI3 equal to 0. So I2 is 8.4 JI2. You can get rid of the J also. So it is minus 4 JI3 minus 15 JI3. So earlier we had written I2 in terms of I1 and I3, right? So if we substitute this I3 in terms of I2 and simplify the equation, we can get in the substitute in the first equation, right? So let us write I3. So I3 is 8.4 I2 is equal to minus 11 I3. So I3 is equal to 8.4 by minus 11 I2. So this particular thing we substitute in equation 2. So substituting in equation 2, let this be equation 3. So it is 85 I2 equal to 9.6 I1, 8.4 I3. In place of I3 we can write 8.4 by 11 I2. So like anyway, now you have 3 equations and 3 unknown. You can start solving these equations and let me know what value you get for I1, I2 and I3. So like I'll be solving in the meantime here. So
Can we
yes.
neglect J terms? Whether it will be correct, ma'am, or we have to use it,
So
ma'am?
this
I
will get
don't get it.
cancelled on the both the sides, right? If we take common
Oh,
here, so 8.4 I2 J equal to, if you take J common here, 4 I3 minus 15 I3. We are not neglecting, we are just cancelling it off.
while substituting in this equation, ma'am, there 85 J I2, There
So
also we can cancel. Okay, ma'am. Okay.
so like in this case there are no constant terms, right? So it gets
Okay.
cancelled. Like you take common and take it towards the right hand side, it will get equated to 0.
Yeah.
So
Okay, ma'am.
only in this particular equation we cannot cancel because it has a constant term.
Ah. Okay, ma'am. Okay.
Yeah. So it is. So now what we will do is we will substitute I2. So we will write I2 in terms of I1. So it is 85. If we bring this term to the left hand side, it will be plus 8.4 square by 11 I2 is equal to 9.6 I1. So I2 can be written as 9.6 by, let's calculate this.
Ma'am, it's minus 88.4 square by 11.
No, like this is minus 11, right? So we have substituted I3. So it is 8.4 by minus 11. When we take this particular term to the other side, like we have to take it to the left hand side, right? So it becomes plus, right? Is it fine?
Yes, ma'am. Yes,
Yeah,
ma'am.
yeah,
Got it.
yeah, yeah. So, so we'll just calculate this. 8.4 square by 11. So it is 91.4145. So 9.6 divided by 0.105016 I1. So let this be equation 4. Now we substitute equation 4 in the first equation, which is 100 minus 16j I1, this equation, right? So it is 100 minus 16j I1 plus 9.6j I2. In place of I2, we will substitute the value. I2 is 0.5, sorry, 105016. So I1 is equal to 100 by 16 minus 9.6 into, so it is around 14.99. So yeah, j will be in the denominator. So this is equal to 14.9918 j I1. So this comes out to be 6.67, and j, if you bring to the numerator, it will be minus j, right? So it is minus 6.67 j amperes. Everyone is getting this?
Yes, ma'am.
Okay. So now can you calculate I2 and let me know? So I2 is just a multiplication of 0.105016 I1. So this is minus 0.7 J, right? Has anyone calculated I3? So, sir, into 8.4 by 11, 0.5349. So these are the three different currents, right? Is everyone clear on this one?
Yes, ma'am.
Okay.
Ma'am.
Yes.
Yes, ma'am. It is clear, ma'am.
Okay. So now you in the question it is asked you have to calculate the potential. Sorry, this is the previous question, right? So V1 and V3 also you have to calculate. So you have all the currents now and you know what will be the voltage drop across the inductor. So V1 and V2 you'll be able to calculate, right? So let me copy the circuit. So can you quickly calculate the value of V2? We have the values of I1, I2 and I3. So could you calculate V1 and V2 and V3 and let me know what is the value? Calculate the RMS value only because the RMS value, we have calculated all the RMS value of the currents. What will be V2?
38.79.
38.79. So V2 is nothing but the self-induced EMF and because of the mutual inductance, right? So it will be 49 JI2 and because of the third coil the mutual inductance that is 8.4 JI3. So we have 49 JI2 is minus 0.7 J and 8.4 JI3 is 0.5439 J. So this J and this J will get J squared which will be equal to minus 1 which will cancel this particular minus sign. So it will be 49 into 0.07. 49 into 0.7. So it will be 34.3 minus 8.4 into 0.5439. It will be equal to 4.56876. Now this J and this J will be equal to minus 1, J square equal to minus 1. So in this case also, so this will be positive and this negative sign will be positive. So 4.56876 plus 34.3. So it comes out around 38.86, which is correct. Okay, this is
Ma'am,
V2. Yes,
ma'am, can we take the sources of left hand side?
yes, you can do this also. Both ways it will be the same value.
Okay, ma'am.
In this case, then you have to do like so current is living in this direction, no? So there will be a self inductance which is 36J I1.
Ma'am, I have written the other way. Other way also I am getting the same value.
Yeah. So just take in that case like the self inductance of this coil and the mutual inductance because of coil 1. So it will be I1 into whatever the mutual inductance is, 9.6. So if you take this, you will get the exactly same value. Anyway, these two particular inductor are connected in parallel, right? So whatever the value in this direction will be, the same value will be in this direction.
But ma'am, I will get minus 38.81 other side.
So let's do it then. It is 9.6. Okay. So it will be in the reverse direction. So it will be like this. So now we have, let's see. So you have to calculate V2. And we have 36GI2 and plus minus 9.6GI1. So V2 will be equal to 9.6GI1 minus 36GI2. So 9.6J into I1 is minus 6.67J minus 36J into I2 is minus 0.7J. This will be equal to, so 6.67 into 9.6, which comes out to be 64.032. This will be minus, and there is the multiplication of j into j square, which is equal to minus 1. Then 36 into
25.2.
0.7. Okay, 5.2. And again, this negative sign and this negative sign will make this positive, and j square is equal to minus 1. So it is 64.076 minus 25.2. So it is 38.87. So it is coming as same, right? The sign is coming same in both the cases.
Yes, ma'am, it is correct. It is coming as same.
So the sign is also same, right? Like somebody had got a negative
Got it,
sign.
ma'am.
Yeah. So you ideally you cannot get the reverse sign. So okay, V3 you guys calculate
8.0235.
8 point. Yeah, 8 point something.
Yes,
So
ma'am.
V3 you can just calculate using this capacitor. It will be easier, like just one calculation. So it is V3 will be equal to minus 15J into I2. Sorry, I3. I3 is 0.5439J. So 15 into 0.5439, which comes out to be 8.1 negative, and J square will be 1 negative, so it is 8.1. So everyone has got this?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. So if you have any doubt, you can ask. Otherwise, we'll move to the next question.
Excuse me, madam.
Yes?
In the first question,
Hmm.
the answer of I1 was found to be minus 2.7 J.
So in this question,
In the first question.
Yeah.
I1 was minus 2.7 J.
Yes.
So RMS value of I1, what should we write? Minus 2.7 or plus 2.7?
So you have to write in like we are writing this in phasors, right? So you have to write plus 2.7. This minus j has to be, if phase angle would have, they would have asked, then you have to convert it in terms of angle. So
Okay.
minus j is actually 0 plus minus 1 into j. That is, the theta will be uh, negative infinity. So it is minus 90 degree.
Okay.
Right? We are writing, note that this is not a constant voltage. This is a sinusoidal voltage. We are just writing in terms of phasor. That is 100 theta. In this case, theta equal to 0 degree. If it was a simple DC voltage given like this, then this is absolute value 100, and whatever the current value you will get, positive or negative, you have to write it that way. But note that this is I bar, not like this is the phasor current.
Okay. Okay.
So this is in terms of like if you have to write the magnitude, this is the RMS value of the magnitude, because the RMS
Okay.
value of the
Okay.
voltage is given.
Okay, madam. Thank you.
Yeah. Any other question? So in all, somebody has unmuted, I guess. Okay. So in all the problems that we are doing now, there is a time varying voltage. So all the calculations that we are doing are either in phasor or in differential equation. Since differential equation are difficult to process, so we end up doing in phasors. Okay.
Ma'am,
Yes.
ma'am, when they will not give the value of mutual inductance, then how will be calculated?
So either the mutual inductance has to be given or the coupling coefficient has to be given. So either of the two has to be given. Otherwise, if it is not given, then assume that they are not mutually connected. Like the flux of this primary winding is not going up to the secondary winding if nothing is given. Like either this has to be given or there will be this coupling coefficient, you know that, right? So whatever the mutual inductance is, it is equal to this coupling coefficient into L1 into L2. Sir has taught this one, right, in his lecture?
Ma'am, I don't know coefficient.
So sir has actually taught this one. So if there are like two inductor, which for the next question actually we will be calculating this coupling coefficient. So wait. So this whatever the flux is like it like you can write it as if this is the total flux, it can be written in terms of the um mutual flux that is getting leaked and the leakage flux. Sir has just referred to his lecture. It is very well explained. Like when suppose it has a common core and there is one winding in which a phi is getting generated, the leakage that is getting not connected to the secondary one, it is written in terms of leakage reactance, leakage flux. And if you calculate the mutual inductance and the self inductance between the first coil and the second coil, you will come up with an expression of 1 minus k 1 minus k2 and all, and which will end up like a particular k coefficient which may vary from 0 to 1 depending on if they are totally coupled, if they are not coupled. K equal to 0 means they are not coupled, k equal to 1 means the entire flux that is getting generated in the first coil is linked to the second coil, which is usually not the case. It like k is always a fraction. So the relation between the mutual inductance and the self inductance is given like this: L1 and L2, if these two are the two coils. So the coupling coefficient can be calculated as m by root over L1 into L2. So either of the three values has to be given. If directly the mutual inductance is not given, this coupling coefficient has to be given. If neither the coupling coefficient or mutual inductance is given, then just assume that the two coils are actually not mutually coupled. But since you have been specifically taught about like the mutually coupled inductances, I guess you will be given the value. Did you find any question where the mutual inductance is not given?
Yes, ma'am.
Okay.
But I have some confusion.
Okay. So see, until and unless they share some common core and it falls within that particular range, they may not be mutually coupled. Like, as a general case, you can write the coupling coefficient like this. You can refer to sir's lecture. I exactly don't remember which number, but it is of this week only. He has specifically derived this coupling coefficient,
Okay,
Ma'am,
okay.
relation.
in the last lecture of the fifth week, he has derived it, ma'am.
Okay, okay, I see. So please go through that, because if I start deriving that, it will take another half an hour and we will be.
Madam,
Yes?
I think m square is k square L1 L2.
Sorry?
M is this m square is k square L1 L2.
I couldn't follow. Yes, k square. Sorry, sorry. Yes, I wrote. Yeah, you're right. You're right. It is k square.
And sir has derived this relation in last lecture of this week, madam.
Okay. So this week,
That is
last lecture.
lecture number 41.
Okay. So whoever is not aware of this coupling coefficient, please go through this lecture, because I remember seeing it in sir's lecture.
Yes, ma'am. Yes, ma'am. Thank you.
Yeah. Okay. Since we started off with coupling matrix, it's good because coupling coefficient, because in the next problem you'll have to calculate the coupling coefficient. So, any other doubts?
No, ma'am.
Okay, then let's move to the third question. So, in this case, there is a secondary and the primary winding is as shown, and the dot convention are such that in the primary the current is entering the dot, and in the secondary it is leaving through the dot, and the mutual inductance is given as shown here. So the first thing that we have to do is calculate the coupling coefficient. So we have just seen the formula, as someone has corrected. It is m square equal to k square L1 into L2. So k is equal to m by square root of L1 into L2. So this is very straightforward, right? Mutual inductance is given as 3, L1 is given as 9, L2 is given as 4. So it is 3 by 3 into 2, which is equal to 0.5. This means whatever the first coil, whatever the flux is getting generated in the first coil, 50% of the flux is getting leaked into this second coil, because of which this mutual inductance is coming up. So in value also you see this coupling coefficient is actually the the amount by which the flux produced in this first inductor is getting linked to the second one. So we have to now, let's look into the problem. We have calculated the coupling coefficient. So now what we have to do is estimate the RMS value of I1 and I2 and estimate the impedance magnitude in ohm as seen from the source. That is, whatever the impedance this particular source is seeing with respect to rest of the circuit. These two we have to calculate. So now we have done two different problems in such way to calculate I1 and I2. So I hope you will be able to do it now. So I would like you to try. So you have to apply KVL in loop 1 and loop 2 and come up with I1 and I2. So I would like you to start it off. I'll give you 2-3 minutes to head start, then we'll start solving it. please apply KVL in loop 1 and loop 2 and calculate I1 and I2. Anyone facing any problem, you can unmute and ask.
Ma'am, what is the polarity of RMS voltage?
So yeah, it will be like this, plus minus.
Ma'am, I1 is equal to 1.173 J amperes, whether it is correct, ma'am?
No, I'm actually getting a different value.
Okay, ma'am. Okay.
Okay. Okay, let's solve it together and see. Like, so
11.85.
Sine and in terms of J, you tell me. The
Yes,
value
ma'am.
is correct. RMS value is 11.85. It's correct. Okay. So since two of you have arrived at I1, let's start solving it then. So in this case, there will be a voltage drop because of self-inductance, 9J I1, and because of mutual inductance, it will be like this, 3J I2. In the second loop, it will be, so I2 is flowing like this. So the mutual inductance is 4J I2 and the self-inductance is the reverse, 3J I1. So KVL at loop 1, so if we move along this direction, it is 80 minus 9ji1 plus 3ji2 is equal to 0. This is the first equation. KVL at loop 2. So if we move along this direction, so it is 3ji1 minus 4ji2 equal to 0. So we have I1 in terms of I2. So we can write it as I1 equal to 4ji2 by 3j. So it will be 4 by 3 I2. Now substituting, so let's like substitute I2 instead. So I2 in terms of 3 by 4 I1. It's the same thing anyway. So now if we substitute I2 in equation 2, it will be 80 minus 9ji1 plus 3 into 3 by 4 I1 equal to 0, right? Eight equal to, so if you bring it to the other side, 9 minus 9 by 4 j I1. I1 will be equal to, so 80 divided by, so if I take 9 common, it is 3 by 4 j I1.
Yeah, ma'am, I am also getting the same value. I have made a mistake.
Yeah, okay. So it is 320 by 27. If you take j in the denominator, it will be minus j I1. Sorry, wait. So it is minus 11.851 j. So the RMS value of I1 will be 11.851. So you guys also have got the same thing. So I2 you can just substitute and get the value. So I2 will be 3 by 4 of minus 11.851.
8.8.
8.8, okay. 8.8, okay. So yeah, so the RMS value will be 8.8. Now to estimate the impedance across as seen by the source, that means we have to estimate the impedance across this terminal. So how will you calculate that? Any
Ma'am,
suggestion?
V by I1, V by
Please.
I1, 80 by
Yes,
I1.
exactly. So okay, sorry. So I'll use a different color. So whatever the impedance Z will be, the source voltage, the phasor of the source voltage by the phasor of the source current. In this case it is I1 because I1 current is flowing here. So it will be equal to 80 by I1 is 11 point. So right now we are not taking the RMS value, we are taking the phasor value. So it is minus 11.85. So we are writing in terms of J, right? So 80 divided by 11.85, somewhat 6.75. And like this minus j, if we bring it to the numerator, it will become plus j, right? 6.75 j. So the magnitude of impedance, since magnitude is only asked, it will be 6.75, right?
Yes, ma'am, it is correct.
Yes. So any doubt in this problem? Everyone got these three problems, right?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. Then let's move to the last problem we have for today, which is estimate the RMS value V0. So until now, like you have seen two different, like you have seen two series circuit and a circuit with a primary and a secondary. In this case, there is a voltage source that is connected across a resistor and two inductors as shown here. So these two inductors are actually in series with opposite like sign dot convention. You have to calculate the voltage across this second inductor V0. Now the voltage that is given, now it is not given in terms of previously it was just given the RMS value of the voltage was given, right? This is given in terms of a sinusoidal voltage. So to solve this, what you can do is you can like convert it into phasor voltages, can't you? So this is some sort of Vm cos of omega into t. In this case, omega is equal to 2. So you can very well convert it into phasor voltage, and then you can calculate and solve the circuit easily, right?
Yes, ma'am.
Okay. So uh, how are you going to calculate V naught? Any suggestions?
Ma'am, we
Apply
can
KVL in phasor form.
Yeah. So you will apply KVL and calculate the current that is flowing in this particular loop. Once you calculate current, you have the value of inductance here. You can calculate, and you have the omega value in the question given. So you can calculate V naught, right? So just out of curiosity, V naught is again in the time domain, right? It will be in terms of cos of some omega t plus theta. So make sure you convert it back. Like for calculation, for ease of calculation, you can either keep it in time domain or convert it into frequency domain, or in terms of phasor and calculate it. It is up to you. So how will we calculate I?
Ma'am, we can converted the instantaneous voltage in terms of phasor voltage.
Yes.
By the in term of sine, because sine 90 minus theta will be cos theta, I think.
Yes, you can even do that. So let's try like can we calculate the impedance of this circuit?
Yes, ma'am.
Yes. So what will be the impedance?
Ma'am, impedance will be XL plus R.
Yes. So to calculate this XL, we need L equivalent, right? So just look, like instead of going to the KVL equation, you can calculate the equivalent resistance. So see, for this second circuit, this case is similar to the second circuit, right? So let me take the highlighter. So yeah, these are the two coils that are connected in series. The dot convention is opposite. So the equivalent inductance in this circuit will be L1 plus L2 minus 2M. You have already know this, right? So can we apply it to the circuit that we have now? Can we? It is the same thing, right? We are writing in terms of voltages, then we are like equating it to the source voltage, and this is the equivalent inductance, right? Is it making sense? Like you can solve using KVL for this particular circuit also, but I'm just suggesting a easier way out. Can we calculate L equivalent in the circuit that we have now?
Yes, ma'am.
So what will be the value of L equivalent?
L1 plus L2 plus 2M.
So please note that the dot convention are in opposite direction. See, in this case, if we assume a current that is flowing here, the same current will be flowing through here. So in this case, the current is actually leaving the dot. So will it be plus 2M? Will it be?
No, it will be minus 2m.
Right, it will be minus 2M. Because you see, for the for the second case we are doing it, right? We had already found it. L equivalent is equal to L1 plus L2 minus 2m. When the dot convention are in the same direction, like as shown in the first case, this is the first case. In that case, L equivalent is L1 plus L2 plus 2m. So is it fine? So we
Yes,
have
ma'am.
the value of L to be the L1 is 1.5, L2 is 2 Henry minus 2 into the value is 0.25, so it is uh, so so it is 3.5 minus 1, 2.5 Henry. This is the equivalent inductance. So can we write now the value of impedance? R is given as 3.5. XL is J into XL, right? So J omega into L. So 3.5 plus J omega is given, like it is given as 10 cos of, like whatever Vm will be this Vm cos of omega t, right? So omega is here 2t. So it is 2 into 2.5. So it is 3.5 plus 5j. This is the value of Z. So can we write, so in order to calculate I, we can convert it to phases. So can we write Z in terms of a magnitude and an angle? What will be the magnitude?
Root under 3/4.
Sorry?
Root under 34 at angle of 59.03.
Okay, so it will be square root of 3.5 square plus 5 square, right? And angle will be tan inverse of 5 by 3.5.
3.5.
So it will be 6.1, I think. Something like this. Let's calculate the angle. 5 by 3.5. 5 divided by 3.5. So angle comes out to be 55 degree. 55.00 something.
Sorry,
But
ma'am.
yeah,
6.1 at angle of 55.0.
yes, that is correct. So this is the value of Z. So can we calculate the I phasor now? V by Z, right? V is given as 10 cos of 2t. So 10 cos of 2t, we can write it in terms of a magnitude. So it is 10 angle of 0 degree, because omega t plus theta, right? And theta is not there, so angle is 0 degree. So it is 10 angle 0 degree.
But madam, we have to write in standard form in form of sin omega t plus theta something. I think so.
So let's calculate I, then we can write it in terms of cos or sine, right?
Okay.
So like V naught t also you can write in terms of cos, right?
But I phasor we are calculating, which is V phasor upon Z phasor. So V phasor it has magnitude as well as angle, na?
Yes, that is what I'm saying. Like
So here we should convert this cos into sin term.
yeah, you can like ideally it would be better if you write in terms of sine.
Okay.
Then your V naught t also you will write in terms of, finally you will get in terms of sine.
Okay.
So like you can write it in terms of standard form, like Vm, so cos of omega t. So if you write in terms of sine of 90 degree plus omega t, right?
Right,
This will
madam.
be cos of omega t. So in that case, it will be this equation will be in terms of sine. So when we reconvert it back to like this I, if you like write it in from phasor to back to the time domain, you will write in sine of 90 degree plus omega t.
Okay.
So you do this way, you will arrive at the same answer. You try it and
Okay.
let me know. Okay.
Okay, madam.
Yeah. So and Z is 6.1032 angle of 55 degree. So this comes out to be so 10 by 6.1032, 1.63 something, 6384 angle of minus 55 degree, because we take it to the numerator. 0 minus 55 is minus 55 degree. So now when I am reconstructing it back, so I am writing in terms of cos, because initially I had taken this in terms of cos, right? So I of t, instead of writing in phasor, I am writing I of t as 1.6384 cos of 2t minus 55 degree. Please note that if you are using the standard notation, standard convention, that is sine of 90 plus omega t, then when we convert like I of t, you will write I of t sine of whatever the angle might be, you will have to write it in terms of that. Okay. So now we have the time varying current that is flowing through the circuit. So it is an inductive circuit with a little bit of resistance. So if it would have been purely inductive, it would have been 90 degree, but since there is resistance, there is some phase angle between the current and the voltage. So this is fine up to this much. So what will be V naught T? So let me copy the diagram once. Yeah. So V naught T will be equal to the net induced EMF across this particular voltage. So it will include the self and the mutual one. So since current is flowing across this direction, the self induced EMF will be L2. In this case it is 2 di by dt, and since the dot convention are opposite, so M will be in the reverse direction. So this will be the self induced EMF, and the mutual induced EMF will be in the reverse sign. So it will be minus of M, in this case it is 0.5 di by dt. So it is around 1.5 di by dt. Now we have the time varying I of t, right? We have found it in the previous page. So 1.5 ddt of 1.6384 cos of 2t minus 55 degree. So if we multiply 1.5 2.4577, so 2.4577, now ddt of this value, so ddt of cos t is minus sin t, right? And then ddt of 2t is 2. Is this fine? Is this okay with you all?
Yes, ma'am.
So this into 2. 4.915. It will be minus of sine of 2t minus 55 degree. Now we will write V naught in terms of cos and we will get rid of this minus sign. So 4.915. So we know sine of minus theta equal to minus sine theta, right? So if you have to get rid of this sign, we can write it as sine of minus of whatever the value is, 2t plus 55 degree. We can write it like this, right? This is sine of minus theta. We can write it as minus sine theta, right? Now we know cos of 90 degree minus theta is, what is cos of 90 degree minus theta?
Sine theta.
So this sine theta, we are writing it as cos of 90 degree minus theta. 4.915 cos of 90 degree minus 2t minus of 2t plus 55 degree. We can write it like this. This is theta. In this case, theta is minus 2t plus 55 degree, right? So if we simplify this, 4.915 cos of, so 90 degree minus of minus 2t will become plus 2t and minus 55 degree. So V naught will be equal to 4.915 cos of 2t plus 90 minus 55 is 35 degree. So V naught t can be written in terms of like this if we write it in terms of cos. Everyone getting this?
Yes, ma'am.
Okay.
Ma'am, but
Yes.
ma'am, but we can also write V naught is equal to XL plus XL into IS.
Could you repeat that?
Ma'am, we can also return the V naught T is equal to XL multiplied by IS or not?
So V naught is only the voltage across this particular inductor. XL will include this inductor too also, right?
Yes, ma'am. It means we can write 2 Henry in terms of J omega L and then
Yeah, and
multiply.
also you have to incorporate the mutual inductance, right?
Okay.
Because there is also a mutual inductance, not just a self inductance.
Yes, ma'am.
So that is why I've like reverted back to the like time domain. Anyway, like we have to write the answer in terms of time domain because you see V naught t is given, not just V naught.
Okay, ma'am.
Yeah. Any other question?
So this is the answer for V naught, madam. It is 4.915 cosine of 2t plus 35.
Yes, cosine of.
So we have to write like this only, na?
Yes, yes.
Okay. Thank you.
Yeah. So, so this brings us to the end of this lecture. If you have any specific doubt, you can ask. Otherwise, like we can wrap it up for today. So in this assignment, you will basically be asked to, like, either you will be given a circuit that has a primary and secondary winding, or it has like kind of different loops, or it may be connected in series, or it may be connected in parallel. Depending on whatever you are given, just take a note of the sign convention and apply KCL or KVL, the basic equations that we have. But note the mutual inductance, okay, looking into the dot convention, because this primarily these assignments is focused on the dot convention. So if you are clear about these these four cases, if you are clear about this, then you can easily solve whatever is given in the question, because the principle is ideally the same. So anyone has anything to ask? Otherwise we can wrap it up for today. Let me see if there is anything in the chat. No. Okay, then I'll stop the recording.
Okay, madam. Thank